Now in this problem, we are talking about two heat pumps and we are going to compare the cost of those two heat pumps. After reading the problem, please try to sketch a diagram detailing what's happening here and then try to come up with a plan to solve this problem. You can pause the video now. Now, according to the problem, we are losing about 140,000 kilojoules per hour and we want to maintain our temperature. If that is the case, we have to supply the same amount of energy from our heat pump. Let's call this as Q dot H. Now our heat pump is operational for 100 hours per month, and for the first heat pump, heat source is 0 degrees Celsius. And our other option is using a lake as our heat source. The lake is at 10 degrees Celsius, and the amount of heat that we have to supply to the house is same as the previous case. Now let's consider that our work requirement for the heat pump is WL when we are using lake as our heat source, and WA when we are using air as our heat source. Let's call the amount of energy that we get from air as Q dot LA and the amount of heat that we get from lake as Q dot LW. And the cost for electricity is 0.105 for kilowatt hour. Now you should know what is a kilowatt hour means. A kilowatt hour is a unit of measure of energy. It is not a unit of measure of power. A kilowatt hour is equal to a kilowatt load running for 1 hour. So it's going to be 3600 kilojoules. The easiest way to find the cost is going to be finding the difference between the electrical energies that we need in these two cases and taking that value into 100 hours. Even though our QH value is same for both cases, because we have different coefficient of performances for these two heat pumps, our WL and WA values are going to be different. So in this case, we don't have any other indication to calculate coefficient of performance. On top of that, we have to calculate the maximum money saved. So maximum efficiencies are achieved when we have Carnot efficiencies. So we are going to assume Carnot heat pumps. If we know the source temperature and sink temperature, we can calculate Carnot efficiencies. In this case, we know temperature of the lake, temperature of air, and temperature of our house. So we can calculate coefficient of performance for lake and air heat pumps. Now that we have a plan, you can proceed with the calculation. Try to solve the question as much as you can before unpausing the video. You can pause now. Now we can calculate coefficient of performance for the heat pump that uses air as its source using our standard coefficient of performance equation. And since we know the energy balance for this heat pump, we can further simplify it and finally write it in terms of temperatures. That is assuming Carnot conditions. Now we can substitute values for TH and TL and then calculate our coefficient of performance. Now remember, these temperatures should be in Kelvin. You cannot use Celsius values. Now you can try to find the coefficient of performance for the heat pump that we uses lake as its heat source. If you were not able to do it on your own, please pause the video and try to follow the same procedure as we did earlier to find the coefficient of performance for lake. You can use the same equation that we used to find coefficient of performance for the heat pump that uses air as its heat source and slightly adjust it. Your value for this coefficient of performance should be 19.87. And now you can find W dot A and W dot L. Now these W dot A and W dot L values are going to be the amount of energy that you need to run this equipment for each case. Now we can calculate difference of cost. If we are assuming 1 hour, we can multiply W dot A by 100 hours and W dot L by 100 hours to find the difference between costs. Now please note that our W dot A value and W dot L value are in kilowatt units. When we multiply this by hours, we are getting kilowatt hours. Since our cost is given per kilowatt hour, we can multiply this value with the rate and get the cost.